Welcome to the community of
engineers, the change agents in the society.
In this video we will discuss reinforced concrete beams. Now how to solve pure bending problem with respect to the reinforced concrete beams when subjected to the bending moment. We know that concrete is very weak in tension, but at the same time very good in compression. Now that is why the steel rods are placed at lower part of the reinforced concrete beams so that to carry all the tensile loads. Further, let the Young's modulus of steel, that is 200 gigapascal, Young's modulus of concrete is 25 gigapascal, and the ratio of the moduli, that is N E S upon EC, that is 200 gigapascal upon 25 gigapascal. So N value, that is 8, means the steel is 8 times stronger than the concrete. Now further, because of the bending above the neutral axis, we observe compression, and below the neutral axis is the tension. Now it is very important to know that what is the location of neutral axis. Now to calculate the location of neutral axis, which is obtained by multiplying its area by the distance of its own centroid. For that, we used to make a transformed cross section of the reinforced concrete beam. Now keeping in view the definition of the location of neutral axis, so we can write as x into b, that is area of the concrete, multiply with the distance from its own centroid, that is x upon 2, minus, now this is the area, that is NAS, now this is the total area, and the distance that is from its own centroid, that is d minus x. Now we can write this as 1.2 bx square plus NAS x minus NAS d to 0. Now it is very important to know the value of this x, and we use quadratic equation to calculate the value of x, that is x is equal to minus b plus minus b square minus 4ac under root upon 2a. Now with this expression we would be getting two values, one positive value of x and one negative value of x, and we use positive value for the subsequent calculations of the maximum values of stress. Now the maximum stress in concrete is calculated by using this expression, mc upon I. Now this m is the bending moment and c is the distance, that is x for the case of concrete. Now for maximum stress value of steel, again same expression, mc upon I. Now here c is d minus x, and to calculate the value of I, that is moment of inertia, that would be moment of inertia about neutral axis, we calculate by this expression, that is 1 upon 3 bx cube plus NAS d minus x whole square, and this is for the top part and this is for the bottom. Now let's solve one example of reinforced concrete beam. We have a concrete beam that is having 4 steel rods, and the width of the cross section of the beam, that is 250 mm, and height of the cross section 450 mm. Young's modulus of steel here is 200 gigapascal. The value of Young's modulus of concrete 25 gigapascal. We have the value of bending moment, that is 200 Newton meter, and diameter of the each steel rod is 22 millimeter. Now with this information we have to find the value of maximum stress in concrete and the maximum stress value in steel. Now to solve this problem we have to first calculate the area of the steel rods. Since there are 4 steel rods, so the area of steel is going to be 4 pi r square. Now pi r square is the individual area of the steel rods, multiply with the 4. So we would be having 4 pi 22 millimeter square. So the value of AS, that is the area of steel rods, that is going to be 1520 millimeter square. Now we have to also calculate the ratio of the modulus, that is N is equal to ES upon EC, that is 200 gigapascal upon 25 gigapascal. So the value of N is equal to 8. Now to calculate the location of the neutral axis, we make a transform matrix. Now in this transform matrix, this is the area of the steel. Now x b, that is area of the concrete, multiply with the distance, that is x upon 2, in consideration with the transformed cross section of the beam, minus NAS multiply with D minus X is equal to 0. Now using values in this expression, X 250 millimeters, B X upon 2 minus NAS. Now value of NAS is going to be, N is 8, the ratio of the modulus, and the area of the steel rods is 1520 millimeter square. Now the value of NAS is going to be 12,160 millimeter square. Now using this value in this place, NAS 12,160 millimeter square, this is in millimeter, multiply with the value of D, that is 450 millimeter, minus X is equal to 0. Now by multiplying this, the value of this is going to be 125 x square plus 12,160 x minus 5,472 plus 0 is equal to 0. Now using quadratic equation to calculate the value of x, that is x is equal to minus b plus minus b square minus 4ac under root upon 2a. So x is going to be minus 12,160 plus minus 12,160 square minus 4,125 minus 5,472 upon 2,125. Now after solving this, we get the values of x, that is minus 263 millimeter and x is equal to 166 millimeter. Since we have to use the positive value of x, so further to calculate the moment of inertia using this expression, INA, inertia about neutral axis, 1 upon 3 bx cube plus NAS d minus x whole square. Now the inertia about neutral axis is going to be 1 upon 3 value of b, that is 250 millimeter, x we have just calculated 166 millimeter cube plus the value of NAS, that is 12,160 millimeter square, and this is 450 minus 166 millimeter whole square. So solving this, we get the value of this is 381.1 19 into 10 raised power 6 millimeter 4 plus 980 into 10 raised power minus 10 raised power 6 millimeter 4, and this is going to be 1361.967 to 10 raised power 6 millimeter 4, or we have the moment of inertia about neutral axis, that is 1361.967 10 raised power minus 6 meter 4. Now we will calculate the value of maximum stress in concrete. This is sigma mc is equal to mc upon I, that is m 200 Newton meter. Now the value of C for the case of concrete is going to be 166 millimeter from the neutral axis. So 166 millimeter upon the moment of inertia we have just calculated. Now that is 1361.967 10 raised power minus 6 meter 4. Now after calculation, the maximum stress in concrete is going to be minus 24.4 kilopascal. Now the negative sign here indicates the compression. Now for maximum stress in steel, that is sigma mc is equal to mc upon I, the value of m, that is 200 Newton meter bending moment, and c, that is going to be 284 millimeter from the neutral axis, and the moment of inertia is 1361.967 to 10 raised power minus 6 meter 4. So the maximum stress in steel is going to be 333.6 kilopascal. So with this we end our discussion.